Hello everyone, welcome back to my YouTube channel. Today we are going to talk about how to perform combustion calculations in DWSIMs. So let's begin with the learning objectives of this tutorial. After this tutorial, you will be able to find out the airflow rate needed for a clean combustion of any given fuel. In this case, the fuel is methane, and also you will able to calculate heat available from the fuel stream. Again, here the fuel will be the methane stream. So let's move to the problem statement that we are going to solve in DWSIM. This is the process flow diagram of the system. This one is the reactor, and here we are taking Gibbs reactor because we do not have reaction kinetics data, and we just simply assume that this reaction happens with 100% conversion of methane. So we have all the information for methane like temperature, pressure and flow rate. Similarly for air, but we do not have the flow rate data for air. And we also have to find out heat supplied by this system. I mean, if 1 kg per hour of methane is burning, so how much is the heat that we can have from this system? So this is one question that we have to answer, and the second one is we have to find out the temperature of hot gases. Okay, so first we have to figure out the flow rate of air using this information. So it's given that 10% excess oxygen is being fed for this reaction. So how we can find out the mass flow rate or the mole flow rate of the air? For that we will perform simple mole balance calculations. So now you can see that it's a balanced chemical equation for methane burning or methane combustion reaction. So ideally 1 mole of methane is required 2 mole of oxygen to completely burn, which form 1 mole of carbon dioxide and 2 mole of water vapor. Okay, so it's given that in air 20% is oxygen and 80% is nitrogen. So we can say that 0.2 mole of oxygen will be present in 1 mole of air. So if 1 mole of oxygen will be present in how many mole of air? So for that we have to divide both sides with 0.2, and for the 2 mole of oxygen will be present in 10 mole of air. Okay, so 10 mole of air is required to burn 1 mole of methane if we talk about in terms of air. So after performing this calculation, we can say that 10 mole of air is required to burn 1 mole of methane. So let's move further. There is another thing, the excess oxygen. So the 10% excess oxygen is given. So how we can include this information with the air flow rate? So this is the simple formula for the excess oxygen, that is equal to mole fraction of oxygen in the air multiplied by the mole of air in the feed minus mole of oxygen theoretically required, that is the 2 mole, and divided by the theoretical mole of oxygen. We have to divide it. So the 10% oxygen is given, so we will find the total air in terms of mole, just rearranging this equation. Okay, so actually we have to find this thing, mole of air which are going to feed when 10% excess oxygen is being provided. So we have all the information. The theoretical mole of oxygen, they are 2, that is 2, and the excess oxygen is 10%, so we are just writing here 0.1 and divided by 0.2. So after solving this equation, we have final answer 11 mole air we have to feed in the reactor in order to completely burn 1 mole of methane. Okay, so let's move to the DWSIM software to solve this problem. Well, now we are in DWSIM latest version. So just start with new steady state simulation. Click next. Okay, now we have to select the components. The first one is methane. The second one is oxygen. Third one is nitrogen. The fourth one is carbon dioxide. And the last one is water. Just reconfirm all the components: methane, nitrogen, carbon dioxide, water, and oxygen. So all the desired components which are participating in chemical reactions, we have just selected them. Then just simply select next, and here we have to select Ping Robinson as a property package. Then click next, and from units I will choose C5 unit set for the calculation of this problem. And now we are ready to construct process flow diagram. So first just take a material stream and then take one mixer. Okay, click on the mixtures, then this new tab will appear. So connect stream 1 and also connect another inlet stream and an outlet stream. Okay, so first change the name. One is methane. Okay, and now just put the all the all the given information. So in that case the temperature and pressure is given. Okay, 25 degrees C and 4.5 bar. I will stop it, otherwise it will continuously calculating and will cause the problem. And the flow rate is also given 1 kg per hour. Now click on the compound amounts. So it's pure methane. Just click just write 1 in front of methane and 00 for all others, and click accept. Okay, then go to the material stream 2 and name it air, and the air is 25 degrees C, 1.5 bar pressure. So before that we just specify the mole fraction of the stream. Methane is 0 here, oxygen is 0.2, nitrogen is 0.8, carbon dioxide 0, water is 0, and clicked accept. Okay, and then again go to the stream condition, and here we have to specify the molar flow, okay, or the mass flow. And we just calculate that for 1 mole of methane, we need 11 mole of air. Okay, so from this one, so sorry, it is 1 kg per mole. So we can see that the molar flow rate of methane is 0.0623346. You just simply have to multiply by 11 with this. Why? Because air flow rate is 11 times of methane molar flow rate. Okay, so I just multiply it with 11 with this number, and then I will insert that value here, and the value is 0.6856806 and press enter. Okay, so and now this is our feed stream which is ready to go into the reactor. Before going to reactor, we just have to specify the chemical reaction that I just simply forgot at start. For that, just click on setting and then go to the reaction tab. Okay, and then click on this chemical reaction, click on conversion, and simply I'm saying here combustion. Okay, and we have to include all the components, all the reactants and the products of this chemical reaction. Also the base component, in this case it's methane, and the stoichiometric coefficient for reactants with minus sign and for product with plus sign. Okay, so for oxygen -2, carbon dioxide is 1, and water is 2. Okay, so you can see that it says stoichiometry is okay, and the equation is balanced, and the heat of reaction at 25 degrees C is also given here. Okay, and this reaction is actually vapor phase reaction, and methane is the base component, and the conversion is 100%. Okay, so we just define a chemical reaction. Now click on the reactors, select the Gibbs reactor and place it into the flow sheet. Click on the reactor, and the in inlet just connect with feed and generate outlets. Okay, so this one, the material stream 4, I will say the vapor. Material stream number 5 is liquid, and this one is energy. Okay, so now just click on the reactor, and the calculation mode is adiabatic. So now the flow sheet has been converged. So now let's see the answer of our first question that was asked here, the temperature of hot gases. So to know that, just click on it here. So you can see that the hot gas temperature is 420 degrees C. Okay, so this is one answer. And the second thing that was asked here, heat supplied by this system. So how we can find it out? For that you just have to simply to calculate exactly how much energy is released from the reaction, simply take the heat of reaction found in the reaction tab and multiply it by the methane molar flow rate. Okay, so from where we can have the heat of reaction? So for that, just come to this flow sheet, go to the settings, and then double click on this reaction, and here you can see heat of reaction kilojoule per kmol with respect to base component, that is the methane. So it is approximately 8 into 10 raised to power 5. Okay, so and the methane molar flow rate is also given. We just calculate it. So we just have to perform this calculation, multiply the methane molar flow rate into the heat of reaction, and then k mole will cancel with k mole, and the units will be kilojoule per hour, and that we simply convert joule per second into watt. So after performing this calculation, we can say that this particular system with methane has the heating value of 13.85 kilojoule per second or kilowatt. So this is the energy content of this fuel stream. So that's all for today's lecture. I hope you learned something new, and it will be helpful for your projects. And if you like this video, please share it and comment if you do have any question. Until next video, take care. Bye bye.